Yes, okay. Um, let's see. So for some reason, the trail manager doesn't work, or not a trail manager, the movement app doesn't work. So whenever I try and run it, it only pops up this kind of little window here. So I'm just going to go over everything else, everything that I've implemented verbally, and try and explain things as best as I can. Hopefully we can get this resolved pretty soon, but I'll do the best for now. So let's start with arrays. I prefer linked lists. There. Okay. So array queues and array stacks. Array queues, I have all the specified parameters, and I added my own rear parameter and a capacity. This is just initialization and sets everything to 0, including rear. Remove that. In queue, if size equals capacity, then resize. So if in queue is called and size is already at capacity, it will resize it. And then it will add the data at that rear element, or it will add the element to the array at rear, which is the back end of it. So it adds this, because this is a queue, so this is first in, first out. If this is an element that's just being added, it's gonna go out last, at least compared to everything else that is already in the array. And this is just a circular buffer where it will update the rear to rear plus 1, module data length, which is actually just like the size, or it's really just like the like the capacity. So if data length is, or if size is less than capacity, that means that everything else will be laid out pretty flat. However, or not necessarily, actually, I should re-say that. If the way that the series of NQs and DQs have happened makes it so that the total number of things that have ever been NQ'd and DQ'd is greater than the size. However, the current size is less than data length. It will allow more elements to be NQ'd at places where old elements have been DQ'd at. So this allows the array to save memory by wrapping around itself. Now, it doesn't give it extra memory, it just allows it to save some memory. DQ, very similar, except it removes the front, actually. Obviously, you can't DQ from an empty list, or from empty array, and this is just a holder, and this holds the value that is DQ'd, and it returns that. And then front is equal to front. This should be -1, actually. Is it? No, it's plus. That's correct. Yeah, that's right. That is correct. Because we're moving throughout the array. Size decreases, and here size increases. Peak, same as DQ, except it doesn't remove anything. It just returns the front. And then it also checks if you're trying to peek into an empty array. So if size equals 0, then obviously you can't peek into something that doesn't exist. Is empty returns if size equals 0. If size equals 0, then it is empty. If size is not equal 0, then it's not empty. Size returns size, clear. It resets everything, resets front, size, and rear. So it doesn't actually clear out any of the old elements, but it allows them to be written over. Resize, it takes in capacity and it sets a new capacity to twice that old capacity, and then temp list, blah, blah, and then this just creates like a temporary list. So with the new capacity, it copies over every member of the old queue into the new queue, and then it sets the old array to the new array, and then so the original old array is actually now dereferenced. Front is now equal to 0, and rear is now equal to size, because now, however, like whatever coiled formation that the old array was in, it's now no longer coiled because there's plenty of space for the array to flatten out. And then we increase capacity. This is just like a system call to print out the capacity and to say that, oh, we just resized it. This is the iterator, and it prints out the value at the index. And this is the array stack. So unlike array queue, it does not have a rear, however it does have a top, which is similar to a front. Push, if size equals capacity, we resize, similar as last time, and then it implements, it adds the pushed element into top, and then it iterates top, and size is also iterated. Pop, if size is, so if the list is empty, you cannot, if the array is empty, you cannot pop from an empty array, or stack in this case. Returns null. It decreases top and size, and it returns top. So top is actually the pointer to the next available space. So when it's decreased, then, well, not necessarily a pointer, but when it's decreased, it is the index of the value at the index of the top value, because before it was the index of the value after the top value. Peek just returns the top value, and you can't peek into an empty list. Return data top -1. Since this top doesn't actually change here, we have to slightly change what we were returning. Is empty, and the size is similar to array queues. I think they're actually pretty similar all throughout. Resize, it's very similar to array queue. It sets a new capacity to twice the old capacity. It sets a new array to have the new capacity, and then it copies all the elements over. It saves the order too, actually, and it sets data to the new array. But the difference this time is, since there's no front or rear, that isn't really something we need to worry about. Clear, it just sets top to 0 and size to 0. And then the iterator is very similar here, where it'll just spew out the next index. List queue is linked list queue is a linked list that serves as a queue that's built in the queue data structure. It has a head and a tail, and it also actually has a size, even though it's a linked list. It just keeps track of how many nodes there are in total. So if we want to enqueue something, then if the head is null, then it actually adds to the head right away. So the head is now, the enqueued item is now the head, and the tail is equal to head. If head is not null, then tail, it adds to the tail. So tail.next equals new node, and then tail equals new node. So sets itself as like the next of tail, and then it resets or it updates tail to point to itself, which is, since it is the latest item in latest edition. And also size is iterated. DQ cannot DQ from empty queue. Pop this holds the head element, and then if head equals tail, then tail is also set to null, because head is equal to, because then right afterwards, so sorry, let me explain. In this case, if head equals tail, that means there's only one element. So we set tail to null, and then we set head to head.next, which is null. So that's what this is for. And then we decrease size, and we return the pop, which is the head element. And here, head dot equals head dot next also works when this is not run, because head dot next is just like the next element in the queue. Peek just returns the head, and you can't peek into an empty queue. Empty size, same as before. Clear, we set the size to 0, and we set the head and tail to null. So we actually dereference the entire linked list. So now all the data that was previously stored here is just lost to the abyss. And this just returns the next item. So next returns the next item. Linked list stack. It's pretty similar to the linked list queue actually, except that it doesn't have a tail. It kind of has a head though, but the head changes every time. So every time something is pushed, new node equal, okay, this is just a holder for the new node. Top equals new node. Wait, is that right? No, that's a little bit wrong actually, because new node next, there we go. And yeah, because it needs to update. New node next equals the top, and then, because I can't actually debug this, I can't tell if there's something wrong until I actually read it, so sorry about that. Anyway, what this does is it sets the next of this newly instantiated node, which holds the element, to top, which is the current head of the linked list, and then the head is set to the new node because this is first in, first out. We want to be able to have quick access to the youngest element in the linked list. Pop cannot pop from an empty stack, and then this holds the top element, and then top equals top.next. If top.next is null, then it becomes null, and size decreases. I thought I already changed this already, but I guess it didn't. System.out. This is just a system call that tells us that we successfully called pop, and it returns the top element that's stored in temp. Peek is very similar to DQ actually, or sorry, very similar to pop, except it doesn't actually like remove the item, and you can't peek into an empty stack. Boolean is empty returns top equals null. Size returns the size. Pop also decreases size. Clear top equals null, and since this is a linked list, it actually just dereferences like everything else, and size just gets reset to 0. And here we are returning the next item. So sorry, we're returning the current item, and then let's do to undo redo manager. Something's wrong. Where? Oh, never mind. It was just like some weird highlighting. Okay. I just saw like a red bar here. Sorry about that. This just initializes all of these as um, array stacks and linked list queues, and this is for both undo and redo. So redo has a array version and a linked list version. Undo has an array version and a linked list version. Record current position. If we're using undo stack, then we would push the undo, and if we're not using undo stack, that means we're using the undo queue, so we will enqueue the current point. Clear redo. This clears it, and clear is pretty simple, but it's explained in the previous source code. Undo. This just calls undo. If we're using undo stack, and then we check if the undo stack is empty, then we just do nothing. We return null. And if it's not empty, then we set temp to the popped value. So undo is like this will return the previous value, the previous state, and then we return temp. But before that, we record, the current position into redo in case we want to redo it. And then, yeah. And then else, if we are not using redo stack, we are using redo queue. So we would enqueue the current position to redo queue in case we want to redo or undo our undo. Else, if we're not using undo stack, that means we're using undo queue, and the same story as before. And this is just like this is then like the same like if else as before, except for undo queue. Redo, very similar. If we are using redo stack, we will set temp to the redo stack.pop. And if redo stack is empty, then we do nothing. Actually, no, this needs to be before. There we go. Yeah, no, this needs to be before, because if redo queue, if redo queue is empty, this is going to become an error. Live debugging. If redo queue, okay, back to here. This is very similar to the previous one, but I'm going to go by quickly. If we're using redo stack, and if redo stack is not empty, we set temp to the popped value of redo stack. And if we're using undo stack, then we push the current value into the undo stack in case we want to undo our redo. Undo our redo, and then we return temp. And if we're not using undo stack, that means we're using undo queue, same thing as before, when we return temp. If we're not using redo stack, then we're using redo queue. And then if we're using undo stack, we will push that current position into the undo stack. And then if we're using undo queue, then we're going to push that into the undo queue. Get undo count, return. This is just returning the size of them. Get redo count, setters. And then if we change the underlying data structure, what this does is it switches. Let's say we change from array to linked list. It moves all the elements from an array to a linked list for undo. And then if it's linked list to array, it switches from the array to a linked list. And I believe queues are inherently linked lists and stacks are inherently arrays in this. Yes, they are. Okay. Yeah, so that's what this is. And then the next one is very similar to that. So I'm just going to run over by one because they're kind of mirrors of each other. use undo stack. It initializes, or it declares a variable here that's going to be used later. So if this the undo stack is, so whatever use undo stack is true or false, if it's not the same as this parameter, then we run. So then we run this command. And so if this is now true, that means that it was false because it's not the same as it was before. So because if this is now true, then we were previously using undo q. So we're transferring everything from the undo q into the undo stack. And then now if use undo stack is false, that means that it was true. So we were previously using undo stack. So we gotta transfer everything from the undo stack into the undo queue. And then there's the same idea for the set to use redo stack. And then these just delegate as necessary. Now for the trail manager, we actually use the custom queue and custom stack here. Add trail point adds, the trail point to, actually first it just initializes the x and y parameter into a trail point thing. So I'll call this a frame. So the frame stores the x and the y pass through, but also collects the current system time, so the time at initialization, and then it puts it into a whatever data structure is currently being used. So if we're using a queue, it enqueues it. If we're not using queue, that means we're using a stack, so it pushes it. Draw a tail. This is a little bit complicated, but we just, actually first, if it's enabled, then we run it. So if it's not enabled, we just don't do anything. We have a current time variable which tracks the current time, and then we use this variable to decide which data structure we're using. So if use queue is true, then we're using trail queue. If use queue is false, then we're using a trail stack. And this is the iterator variable, or the iterator class that's found in all the data structures that we have looked at so far. So while there is a next, it will add I think this is a rectangle, I believe, and it will actually make the rectangle fade over time, and which is why we need this, so that we know how old the rectangle is, because it also keeps like the timestamp here. Clear all points. This actually just calls two other functions. So if you were using queue, then we use clear all points for queue. If we're not using queue, then we use clear all points for stack. But it does pass through a current time, so we don't have to calculate that again. And clear all old points for queue, while the trail queue is not empty. We hold the oldest value, which is just the peak, and because we don't actually want to pop it if we don't need to. And then if it does turn out that value, the oldest element is too old, we will dequeue it, else we just continue. And then for stack, it's pretty similar, except actually it's a little bit more complicated because the stack is harder to find the oldest element. So what we actually do here is we make a whole new stack, and then we straight up just empty the original stack, trail stack, into this new stack. And for each member, we basically check if it is too old, and if it's not too old, we just add it back to the original stack. Enabled. If this is just not enabled, it'll clear out everything. and then it'll clear the respective data structure. And this is just delegation, trail point. We assign this dot x to x, this dot y to y, and this dot timestamp is timestamp, and timestamp is usually given on call. And let me see. Move app. Yeah, I don't know what's going on here, so I just did the best I can. Like, it just runs this kind of blank screen. It doesn't even close properly, actually. And then here, when I try and run it here, this is the configuration I made for it. And here's just like the settings for the configuration. It's not really that complicated. Is the applications.movement app, and then we have the folder that we're working in here. And I also had to like color this a little bit. So I had to set this to source code and set the resources to resources, which is very helpfully named. And also set the images. Oh, I tried setting the images to resources, but I just still didn't use it. And I'm not sure if this is supposed to be like this, but I can't undo this. So correct, because right now this is excluded and I can't unexclude it. But oh well. That is it for the video. It's a very long one. I'm terribly sorry because I can't demonstrate. But yeah.